Okay, so let's get started. So I'll just pick up where I stopped yesterday, which was we introduced superspace and superfields, a more powerful and compact way to describe supersymmetry multiplets and their transformations. Okay, so just to remind you, yesterday we defined what superspace is. So superspace is the regular space-time augmented by cross-bound coordinates, theta and theta bar. Okay, so theta and theta bar are the superspace part of the coordinates. And the reason we introduced them is so that we can represent the supercharges as derivatives in these superspace coordinates. And so we showed that if we define these differential operators acting in the superspace coordinates and also the regular coordinates, so if we define these superspace differential operators, then they satisfy the same algebra as the supersymmetry algebra. So 2 sigma mu alpha dot. Okay. So then we can represent an entire supermultiplet as a function on superspace. And that we call a superfield. Okay, so I define it as a general function on superspace. Then if I expand this out in components, so that's what we say we expand this out in a superfield in components, that means to look at the expansion of this in theta bar, then the coefficients of that expansion are going to be regular fields that are just functions of x. Okay, and all those fields will live then in the same supermultiplet. Okay, so so if we just take a general function of x theta and theta bar and expand it out, that's going to give us the general superfield, and so that's where we stopped last time. We wrote out all the parts of the general superfield. And so somebody asked at the end of yesterday's lecture whether I suppressed some indices here, and so that's common. So I'm not going to write all the indices out all the time. So whenever you see something like this, implicitly the indices are being contracted like that. Okay. So because I started out with this spin 0 field here, everything else here should also be spin 0 just to make sense. Okay. So all the components of this, like this. All right, and so this is the general superfield. Okay, and so why are all of these component fields part of the same supermultiplet? It's because once I've represented the theory in superspace with these supercharges being derivatives like that, then the transformation by supersymmetry, so the transformation is in general the commutator of the field with respect to the supercharge, then that is the whole point of doing this here, is that we can represent this transformation as a derivative acting on phi in superspace. And so you've all seen this before when you've talked about translations, right? You have a similar formula for translations in regular QFT, where you have the momentum operator here, p mu, and it corresponds to a derivative of the field just in regular space-time. Okay? And so we also have this. Okay. And remember, these are the transformations of the field under supersymmetry. All right. So, does anyone have any questions about that? No? So maybe it would help if I worked out just a quick example. Okay, so for example, let's just consider the transformation. What does this set of equations imply for the transformation of the general superfield? Just the lowest component, let's say. So the lowest component of the general superfield, it's that bottom component, is the scalar field phi. Okay, so we know how phi transforms under supersymmetry, right? We did that last time for a general superfield. Phi transforms under supersymmetry into psi and psi tilde. Right? If I transform with the left-handed supersymmetry, I get here. If I transform with the right-handed one, I get here. Okay, so let's just see how that's reproduced by this side of the equation. So that's just a straightforward calculation. We have delta alpha phi is equal to q alpha as a derivative acting on phi. And so that's d by d theta alpha minus I sigma mu theta bar d mu. Alpha. Sorry, acting on phi. Okay, so if I were to do this calculation in full, what would I do? I would act on this equation here, right, with this differential operator. So that's just a straightforward calculation. We just have to be a little bit careful about differentiating with respect to Grassmann coordinates, right? We have to, there's some minus signs you have to keep track of, but that's straightforward. And that would give us then we would match order by order in theta and theta bar the left-hand side and the right-hand side. Right? So on the left-hand side we have delta alpha phi plus theta delta alpha psi plus theta bar delta alpha psi twiddle. Right? So on the left-hand side we have the transformation property, the transformation of all the different component fields. And on the left-hand side, we have the transformation properties of all the component fields, and on the right-hand side, we have what they transform into. Right? So we just match the same powers of theta and theta bar. Okay, so, and you get that from acting with this. All right, so if I do that, for instance, for the lowest component, so what's the lowest order in theta and theta bar? The zeroth order in theta and theta bar. Well, if I stare at this for a second, I'm not going to get it from this term. Right? This term is theta bar. So this term is always higher order. I'm only going to get it from this term here. And it's only going to come from when that acts on the theta side. Okay, so this is just equal to psi plus higher orders in theta and theta bar. Right, so where would the order theta come from? It would come from here only. It would come from this derivative acting on this. Right? So we would have, I'm not going to keep track of factors of 2 anymore. So we would have theta f. Okay? So this is what we know. We know that phi transforms into psi, and psi transforms into f. Okay? That was the, if you recall, that was the diamond I had before. I had phi, goes to psi, goes to f, and the rest of the diamond. Right? Okay, so I can keep going and all that, but let me just stop there. Okay? All right, so that's how the supersymmetry transformations work, and we applied it for a general superfield. Now, to build supersymmetrical ground chains, what we really want is the chiral superfield, because that, we think, describes matter fields in the NSSM, for instance. So, for a chiral superfield, is there any question? Maybe I should stop. Is there any question? No? Okay. So for a chiral superfield, we need to truncate this thing to just the scalar and fermion and this auxiliary field. Okay? So, yeah. So we need a superspace analog of the constraint that we came up with last time, which was the supersymmetry transformation, the supersymmetry, right-handed supersymmetry transformation of phi is 0. Okay, so what would your first guess for this constraint in superspace be? It would probably be that, so is it Q alpha dot acting on the whole superfield equals 0? That would probably be your first guess for what the superspace constraint would be, right? So why not just, we know that the supersymmetry transformation is given by the super derivative thing acting on the superfield, right? I'm going to be saying super a lot. Okay, so acting on the superfield. But so why not just promote this whole thing to superspace directly? Right, so this is not correct, okay, because it gives you too much. This would actually imply that the entire, like all the components of this thing transform under the right-handed supercharges to 0. Okay, whereas all we want is the lowest component transforming to 0. Okay, so this is incorrect. So we only want phi to go to 0 under Q alpha dot. Okay, whereas this would imply all the components of the superfield, supermultiplet, transform to 0, which is not what we did last time. That's not true. Okay, so we need some other way to impose this constraint. Okay, we need some other way to impose this constraint, some way of setting something to 0 that implies that the lowest component of phi transforms to 0, but not the rest of phi. Okay, so I'm going to erase this now. So what we need okay, so I'm headed towards something called the supercovariant derivative, but so let me motivate it one other way, which is so we want the lowest component of phi to transform to 0, and notice that when we did this calculation for the general superfield of how the lowest component of phi transforms, it actually didn't care about this extra thing we had here, right? It only cared about the d by d theta. Okay, so that suggests that we need some other object that's not this Q that also starts with d by d theta and maybe has something else here. Okay, so all right. So if you are not following this motivation, it's okay. Let me just introduce the answer and then explain how it works. Okay, so we need some other way to impose the constraints. Let's see. Yeah, so we need some other way to impose the constraint, which looks like a supercharged derivative thing. Okay, it has the same d by d thetas, but differs here. Okay, and so that's something called the supercovariant derivative. Okay. So these are called the super covariant derivatives. And you know, operationally, all I did is I changed these signs here. Okay, so they agree in the d by d thetas, but they differ here, but only by a sign. And so why the heck did I do that? So I claim that the constraint I want to impose for a chiral superfield is d alpha dot on the superfield phi is equal to 0. Okay, this would have the desired effect of setting the supersymmetry variation of phi to 0 under the right-handed supersymmetry transformation, but not any other components of the supermultiple. Okay, because this is not the same thing as q alpha dot. This is not the desired effect. Okay, but so that would explain this d by d theta dot. But what fixes this coefficient here to be plus this? Why is this not like 7 times theta sigma mu d by dx mu? So what fixes the coefficient to be exactly plus? Well, the clue is in the name of this object. It's called the super covariant derivative. And if you think about what this constraint means, right, it had better be consistent with supersymmetry. Otherwise, so what does it mean to be consistent with supersymmetry? So it had better transform covariantly under a supersymmetry transformation. That is to say, if I hit this with a supersymmetry transformation, then the constraint I impose should look the same, you know, in the transformed frame, right? Otherwise, it would not. Otherwise, the constraint would sort of break supersymmetry. Okay. Otherwise, the constraint would select out a specific supersymmetry frame, if you like. Okay. So, what does it mean to be covariant with respect to supersymmetry? Does anyone know? So, what does it mean to be covariant with respect to supersymmetry? Or for this thing to be consistent with supersymmetry? That's exactly right. So it should, well, not exactly commute, but this is a fermionic thing. So it should anti-commute with supersymmetry, with the cubes. Okay, so covariant requires that d alpha dot with q alpha dot is equal to 0. And etc. for all the others. So all of the anti-commutators of all the d's and d twiddles with all the q's and q twiddles should be 0. Okay, so then it's a covariant thing. And so requiring this fixes this coefficient to be +1 and +1. Okay, so you can, this is another easy homework exercise, is to check this at home. Okay, that'll give you some practice manipulating these thetas and theta bars. Okay, so that is what a chiral superfield is defined to be. And if you impose this constraint, then you find, so that eliminates all the components of the chiral superfield except the one that we want. So for chiral superfield, with this constraint, you end up with just the parts that you want. Okay, you end up with the scalar field, the fermion, and the auxiliary field, and nothing else. Okay, and so you see also a nice thing about a chiral superfield is that it's holomorphic in the thetas, at least for the parts you care about. Anything that depends on theta bar, there are theta bars here, but they're all derivatives of the fields you started with. Okay? So the independent degrees of freedom here are all multiplied by only phases. Okay, so that's a special property of these chiral superfields, which are in some sense half of the superspace. Okay. Good. Any questions about this? Too early in the morning? Okay. So I can also define an anti-chiral superfield in the same way, which is something annihilated by d alpha. All right. And remember, products of chiral superfields are still chiral. Okay, so we saw that before with the supersymmetry transformations, and here we see it's also totally trivial because we define the chiral superfield using a derivative operator, right? The derivative constraint. So with a product of chiral superfields, the derivative, is still true. The derivative is still 0. Okay. And if I take a product of chiral and anti-chiral superfields, I don't get anything special. That's just a general superfield all over again. Okay? I can also mention one other interesting side bit about chiral superfields. So here we have a structure, okay, products that has, so products of chiral superfield is still chiral, and sums of chiral superfield is sums and products of chiral superfields are still chiral. So what mathematical structure does that define? Anyone with some math background? Something which has both multiplication and addition? Yeah? Anybody? A ring. A ring, thank you. So, so this defines what's called the chiral ring, which has interesting applications in more formal studies. And one cool property of the chiral ring that you can prove is that all correlation functions are trivial. Okay, so that's a quick one-line proof. This is really a side note, but it's a neat fact about the chiral ring. So suppose I consider the correlation function of any number of chiral, just purely chiral operators. Then the claim is that this thing is independent of all the positions of these chiral operators. So independent of the xi's. And in particular, it means I can take any one of these to infinity, and by the cluster decomposition principle, this thing should factorize into just one-point functions. Okay? And so it's a cool application of this formalism to show that this is true. Okay? And it takes basically no time. So let's just consider the first one here. Okay? So the claim is that this thing is independent of x, of x1. And so another way to say that is that the derivative with respect to x1 vanishes. Okay? So let me put a d mu here. The claim is that this is equal to 0. Right? And but what is the derivative? It's the commutator of a q and a q bar. Right? So the derivative is the commutator of a q and a q bar acting on this phi. Right? And so when the q bar is acting on the phi, it's 0. Okay? And when the q is acting on the phi, then I can integrate by parts, if you like. I can move the supercharges around because the vacuum is invariant. have the Q bar act on one of the other 5s. Okay, so that shows that this thing is 0. So, okay, I was a little bit sloppy here because I'm working with the superfield, so this makes more sense for the lowest components. But I can prove something similar for the superfields if I use the supercovariant derivative here instead of the Q's. Okay. All right, so that's what I wanted to say for now about chiral superfields. We can also define, okay, so that's chiral superfields. We can also define a vector superfield, which contains all the components of the vector supermultiplet. And just trivially. So we take a general superfield, call it V, and we require that it's real. Okay, and so then all the components of V are the components of a vector supermultiplet. Okay? And we're not going to use it probably in the course, but I also talked about the current supermultiplet. Okay, the real linear supermultiplet. And that can also be represented as a superfield, which is an object J which satisfies J equals J dagger, and D squared J equals 0. Okay. So it's very straightforward once you get used to it to translate between the supermultiplets and the Q's and the superfields and the D's. Okay. All right, so that finishes our construction of the basic supermultiplets. Basically, the chiral and vector is all we're going to need going forward. And these are the ingredients then of building any supersymmetric theory. Okay? So if you have any questions about that, that would be a good time to ask. The next thing I'm going to do is to construct the Lagrangians, supersymmetric Lagrangians. No, okay. All right, so yeah, so the next step in the story is to construct Lagrangians that are invariant from the supersymmetry. Okay. So I'm going to do this in 2 parts. I'm going to first talk about SUSY Lagrangians without gauge fields, because that's simpler, a lot simpler. And then I'm going to talk about how we put gauge symmetry into the story. Okay? So, chiral superfield only. And now. So how do I build a supersymmetric Lagrangian out of just chiral superfields? Okay? So what does it mean for the Lagrangian to be supersymmetric? Its transformation under, so what does it mean for the theory to be supersymmetric? The transformation of the action under supersymmetry had better be 0. So this had better be true. Right? Okay, so as is the case with any symmetry, S is the integral of the Lagrangian, and so this becomes a requirement that the Lagrangian transforms to a total derivative. Right? We allow for total derivatives. Okay, so we need that. If I put L's here instead of S's, this transforms into a total derivative. Okay, so that's the basic requirement for a supersymmetric theory, is that the Lagrangian under transformation of supersymmetry goes to a total derivative. All right, so okay, so I probably should have said this earlier, but so what do we have at our disposal that has this property that transforms into a total derivative? Okay. Yeah. So how do I get something that sort of automatically transforms into a total derivative under any q or any q twiddle? So suppose I have a general superfield. So suppose I have a general. So what do I have to do to that superfield in order to? So what do I have to do to that superfield in order to guarantee that the transformations of it under supersymmetry are total derivatives? So okay, so the answer is that this thing transforms into a plane derivative. Okay, I'm going to be a little sloppy with the notation here. When I write q acting on phi, that really means the commutator of q with phi. Okay, which as we saw before is the super-covariant derivative acting on phi. So there's a bit of notational sloppiness here. I don't want to keep writing these commutators. Okay, so the claim is that q to the fourth on anything transforms into a total derivative. Okay, what do I mean by q to the fourth, by the way? So this is like the most you can transform anything by supersymmetry before you run out of steam, basically. Right, so q to the fourth here is defined to be q alpha, q tilde alpha, dot q tilde alpha dot. So let's think about what happens if I try to hit this with another supersymmetry transformation. Okay, what happens if I try to hit q to the fourth with another q alpha or another q tilde alpha dot? Okay, so what happens if I try to hit it with a q? Anybody? I get 0 because there are 3 q's here, and there's only 2 to work with, right? Good. And what happens if I try to hit it with a q tilde? This one's a little harder. It is a total derivative, and why? So, okay, let me go a little slower. So q, if I hit this with any q beta, let's say, that's 0 because I have 3 q's next to each other, right, and the anti-commute. Okay, so if I try to hit it now with a q tilde beta dot, it's a total derivative. It's a total derivative, and the reason is, so it's a little harder to see, but the reason is that I want to make it 0, right? That's where I would like it to go. I would like it to go to 0, but it's in the wrong order, right? It's only 0 if the q tilde is next to these other q tildes, right? Then they all meet each other and then they. Okay, so in order to get it over to here, I have to anti-commute it through these q's, and there I use the supersymmetry algebra to do that. And I use the supersymmetry algebra, which is q tilde equals a derivative equals p mu, right? So anytime I anti-commute it through, the price I pay is a derivative. Okay, good. So q to the fourth is something which always transforms either to 0, which is also 0 is a total derivative, right? So either it transforms to 0 or it transforms into a total derivative. Okay, so it has the desired properties. Q to the fourth of anything. Good. And now I define q to the fourth in this way as q squared and then q tilde squared. What would have happened if I'd done it in any other order? Like, why did I choose this order and not q tilde, q tilde? Why did I do that? Anybody? Is there anything special about this order? Or maybe it doesn't matter. They differ by total derivatives, right? I can reorder the q's and q tildes so I'm blue in the face. On only the price I pay is a total derivative at most, right? Okay, so the order doesn't matter. For these q's and q tildes. Okay, good. So here we have our first stab at a supersymmetric Lagrangian. So if I write L is equal to q to the fourth of any general superfield, is supersymmetric. Okay. So another way to write this. Okay, another way to write this is in superspace. All right. So maybe you've seen it in superspace before. So this is how you write it, sort of in components, if you like. So let me also say what this is in superspace. So remember, Q is like d by d theta, Q plus stuff, and Q twiddle is like d by d theta bar plus stuff. Okay? And so what the Q to the fourth is doing in superspace is it's selecting out the highest component of phi. The highest component is the theta to the fourth component. Okay? So this is also equal to the theta to the fourth component of the superfield. Okay? This is also called the D component. It's also the highest component of phi. So if you recall, I wrote the general superfield as this diamond, right? Right, it's this diamond, and the top component is what I call D, so that's why it's called the D component. Yeah, so it's the last thing you get from this diamond, and then after that, it's all total derivatives. Okay. All right, so this is not a very satisfactory Lagrangian, in particular because our general superfield is a reducible multiplet, right? We'd like our particles to fall into the irreducible multiplets, the smallest multiplets. Okay, so we should be talking about chiral superfields. And so for chiral superfields, remember the product of a chiral and an antichiral superfield, or any number of chiral and antichiral superfields, is a real superfield. Okay, so for just chiral superfields, let's say I have a collection of chiral superfields phi I. Okay, then I can consider a general function of phi I and their daggers, and this thing is just a regular general superfield. Okay. And so my Lagrangian could very well be this thing, theta to the fourth. Okay, and so this is called the scalar potential. and it includes the kinetic terms for all the fields. And I will work that out in a little more detail in a moment. Okay? So this is called the Kähler potential, and it's one ingredient to a supersymmetric Lagrangian, and it contains a particular role of kinetic. There's another way I can write this theta to the fourth, taking the theta to the fourth component, which makes it look nicer. Doesn't have any other effect, it just looks nicer. And it's how people normally think about superspace and supersymmetric Lagrangians. So what is a fact about, so this is like taking four derivatives with respect to thetas and theta bars. And what is a curious fact about Grassmann coordinates is that derivatives and integrals are the same. Right? So a curious fact about Grassmann coordinates is that this is equal to the integral and the derivative are the same thing. Right? So we all learned that in first grade, right? Okay, so I can do the theta to the fourth component. I can write this in a nice way. E2 theta, sorry, E4 theta. Okay. I can write my Lagrangian as the integral over all of superspace of the Kähler potential. So that's why this thing is called a potential, right? Because some number of derivatives of it or some integral of it is equal to the Grassmann, gives me the thing that I want the Lagrangian. Okay? And so this has another nice expression, which is that the action is now the integral over all of superspace of K. Right? The Lagrangian was the integral over all of space, and it's also the integral over all of superspace of something else. Sorry, the action was, the action was an integral over all of space. It can also be thought of as the integral over all of superspace of some other form. Okay? All right, so okay, so let me mention one other property of the Kähler potential that is sometimes useful. So K is, sorry, not K, the theory is invariant under what's called Kähler transformation, which is where I shift K by K plus any function of phi plus its dagger. Okay, so what does that mean? So what's going on here? So I'm using here a more basic fact. So maybe I should step back. And so we're going to need this also in a moment. So suppose the Kähler potential had just been a function of phi, no phi daggers. What would this integral d4 theta give me?
0.
It would give me 0, or it would give me a total derivative. It depends on what order I act with the q's, right? Okay, good. So if K were just a function of phi or phi dagger, then integral d4 theta of K would be a total derivative. Okay, so it really has to be a function of both phi and phi dagger for me to get something non-trivial. Okay, so that is what's underlying this claim here, which is that if I shift K by any function of phi dagger, right? Then these things under d4 theta just become total derivatives and don't contribute to the dynamics of the theory. Okay, so the theory is invariant under these shifts. Okay. So the theory, which means the action, is invariant under the scalar transformations. Okay. So this is a good segue into the other ingredient of a supersymmetric Lagrangian, which is called a superpotential. Okay, and it involves just a function of phi or just a function of phi dagger. Well, it involves just a function of phi. And you add its complex conjugate. So suppose I want to just use phi in on phi dagger. Can I do anything with that? Okay. If I were just a general superfield, the answer would be no. But phi is this parallel superfield which obeys this constraint. So I can construct one other thing which is automatically supersymmetric. So claim if phi is a parallel superfield. So we saw that q to the fourth on phi gives me a total derivative, so that's not interesting. So it means I tried too hard, right? Too many q's, and I got essentially 0. So I don't want to do that. I want to get something which is non-trivial, but if I hit it with any more q's, I get 0. Right? I want the step before that. So it's not q to the fourth on phi that I want, but the claim is that the q squared on phi transforms into a total derivative. Okay, q to the fourth was too much. Okay, but the claim is that q squared phi is not a total derivative by itself, but under the further action of q and q twiddle goes into total derivative. Okay, so how do we see that? It's the same. It's the same way we did it for the general superfield in q to the fourth. So consider if I act with q, what is that? It's just 0. There are 3 q's next to each other, right? And if I act with q twiddle, it's not 0. But what happens when the q tilde gets all the way here? This is a parallel superfield, so it's annihilated by q tilde transformations. Right? So I want to bring this here to get 0. The price I pay is, again, the anti-commutator q tilde and q, which are the total derivatives. Okay? So this is the second type of term that we can add to a supersymmetric Lagrangian built out of parallel superfields, which is q squared of any function, q squared of any function of phi, and not phi dagger, is supersymmetric. Okay, which I can also write as the theta squared component, W. Okay, so now my Lagrangian will contain this term and also this term. Okay, this is called the superpotential. So my most general supersymmetric Lagrangian for parallel superfields is made of a Kähler potential integrated over all of superspace, and a superpotential integrated over half of superspace. Now, the Lagrangian has to be real, right? To describe any physical theory, physical system, I mean, the Lagrangian has to be real. So we always add to this the complex conjugate. which is also the integral d2 theta bar of w by that. Okay, that's how you do the complex conjugate. And so also the Kähler potential should enjoy a reality condition. The Kähler potential should be zero. That's also why I did this Kähler transformation here to respect the reality of K. Okay. Any questions? Yes?
Sorry, going back to your Kähler transformation, is that a function of phi complex phi dagger, or is it a function of phi dagger?
Yeah, so you think of it as the complex conjugated function of phi dagger. Yeah.
Okay,
Is that too many daggers? No, I think that's what I mean. Yeah.
Okay.
It's literally this thing dagger, star. Yeah. Okay. So the whole thing is still. Okay, so let me collect all the pieces together, put them all in one place. Okay, so my most general supersymmetric Lagrangian for chiral superfields is L is equal to integral d4 theta plus integral d2 theta of u phi plus the complex conjugate. Okay, so this is called the West-Zumino model, also called the non-linear sigma model, for reasons that will become clear in a moment. Okay. Sometimes the words West-Zumino model are refer just to the renormalizable version of this, and then the most general version, including non-normalizable terms, is the nonlinear sigma model. But sometimes people just call the whole thing the West-Zumino model, just for any model that just has chiral superfields. Okay, so I introduced now the term renormalizability, and so let's also think about what form this has to take for a renormalizable theory. Okay, very often we don't just study renormalizable theories, right? We do effective field theory, so we don't care. There are non-normalizable terms. But sometimes we just want to study renormalizable theories. And in that case, this West-Zumino model becomes very simple indeed. Okay, so what is the condition for renormalizability? What is the condition for that this Lagrangian is renormalizable? I'm sure you know the answer. Yes? Sorry? Dimensionality of the operators, right? So all the operators in a renormalizable Lagrangian should have dimension less than or equal to 4. Right? Okay, so let's apply that constraint to K and W. So let's do a little bit of dimensional analysis. But for that, we have to go back and understand what are the dimensions of theta and theta bar. So a little dimensional analysis. Yes. So there's a number of ways you could do this. Maybe the simplest way is to just look at the expansion of the superfield in components. Right? So for a canonically normalized scalar field, the dimension is 1. So this dimension is 1. For a canonically normalized fermion field, the dimension is 3/2. So that tells us that theta and theta bar have dimension -1/2. Okay. So now comes the slightly confusing thing, right? That the dimension of d theta is equal to minus that. But we're used to thinking of the dimension of dx as the same as the dimension of x, right? the dimension of d theta is actually the opposite of the dimension of theta, because you have because d theta is really the derivative. Right? So the dimension of d theta bar are both plus a half. So now I come back to here, and I see that d4 theta involves, gives me already dimension 2. Right? So this already has dimension 2, which means the Kähler potential should have dimension 2. This has dimension 1, which means the superpotential should have dimension 3 for a normalizable theory. Okay. So notice also that the dimension of a Caros field, since it starts with phi, is also this 1. Okay, so if I build K out of a polynomial, or a Taylor series, in phi and phi dagger, and I'm only allowed to go up to dimension 2, okay, what's the most general K I can consider to keep the theory renormalizable? So I could have just a constant, so that's trivial, right? I could have phi, I could have phi dagger, I could have phi squared, phi dagger squared, and phi dagger phi. Now, which of these terms actually contributes to the theory? Which of these terms gives you something non-trivial?
The last one.
Only the last one. Right? All of these other ones, why are all these other ones, why do all these other ones not matter?
transformation.
They're just, they could be removed by a Kähler transformation, or in other words, they're just functions of phi, just functions of phi dagger, so they, after the d4 theta, they become total derivatives. Okay? So none of these matter, and so we see that the Kähler potential for renormalizable theory is completely trivial, just has one term, if I only have one field. And more generally, if I have a number of fields, it's number of constants Dij, phi I dagger phi j. Okay? And the superpotential is dimension 3, so it can be some fi phi I plus a half Ij phi I phi j plus 1/6 lambda ijk phi I phi j phi k. Okay? This is the most general renormalizable Westphalian model. Okay, so, all right. So, and we can do one last thing to simplify this without loss of generality, which we can always do in a field theory, right? Which is to canonically normalize things through a unitary transformation. Okay? So this is some Hermitian matrix here because the Kähler potential has to be real. So by doing a unitary transformation on the phi's, I can just make this thing diagonal. Well, a unitary transformation and an overall rescaling, if you like. Yeah. So a unitary transformation and then a rescaling with eigenvalues, I can make this thing just the identity. And this is called the canonically, so this is called the canonical Kähler potential. And as we'll see next time, this is what leads to canonically normalized kinetic terms for all fields. Okay. So I guess I'm out of time. Let me just comment here on what these different terms mean. So I haven't showed you why, but this contributes to the kinetic terms, and only the kinetic terms. Okay, which makes sense because it has no dimensionful parameters or anything, right? So it's well suited to become the kinetic terms. So all the dimensionful parameters and all the other parameters of a theory are going to come from the superpotential. Okay, so here you see the mass parameters. These are dimensions of mass. So these are going to set the masses of all the chiral superfields. Remember, a chiral superfield has inside of it a scalar and a fermion. Okay, and so in supersymmetric theory, the scalar and the fermion are all going to be set by these the same ends. Okay, and then these, what are these lambda ijk's? So they're going to give rise to all the interactions of the theory. And this is a normalizable theory we're talking about. So what kind of interactions can you have between scalars and fermions that are normalizable? So you can have phi cubed, phi to the fourth, and Yukawa couplings. Right? So that's what these are going to give rise to. Is well, these are going to give rise to phi to the, these are dimensionless couplings. This is going to give rise to Yukawa couplings and phi to the fourth. And some combination of these are going to give rise to phi cubed couplings. Right? Okay, so we're going to work all that out in some detail next time. I think I'm supposed to stop now, right?
I think you have half an hour.
Oh, okay, we start at 9:30.
9:30.
Oh, okay, thank you. Okay, we're going to work that out now. Yes, good. All right, so this was all in super space and super fields. I was going to say mistake yes.
So, you said the function scale, it's transfer field, and we can think of it as a Taylor series. So, in terms with covariant and super covariant derivatives, are including the Taylor?
Oh,
you come from d alpha and psi tau and
yes, so that's true. I left out, good, thank you. So I am making a slight mistake here. So if this is normalizable, then everything I told you is indeed the most general thing. But yeah, I left out, thank you. So I left out, okay, so I think what you're saying here is that d to the 4 theta of anything is supersymmetric. Yeah. So it's not enough just to consider like a polynomial implied phi dagger. Okay. I should also consider supercovariant derivatives of phi and phi dagger as long as they're an Ransome variable. Right? So for instance, other terms that I can add to this Lagrangian and that are in general present in an effective theory are things like d squared, say phi dagger phi. Right? That's an example of something you're asking about, right? These things are in general present in effective theory, but yeah, in a normalizable theory, they're not there because they're all higher dimensional derivatives. Yeah. Okay.
But then usually when people talk about the Taylor, they are not thinking of these terms.
Yeah, so the terminology is that the Taylor potential refers to no supercovariant derivatives, and then everything else can also be there. These are just general D components. General D terms. Yeah. Totally. Okay, so but this thing here with the K's and the W's is called the nonlinear sigma model. So for most general effective Lagrangian can also, or should also, add terms involving the supercovariant derivatives. Okay. Thanks for catching that. Okay, good. Any other questions? No. All right. So we've been working with superfields and that formalism, and you see how nice it is, how compact everything is, right? But yes.
Sorry, can you repeat why you don't put dagger?
In W? Oh, yeah, because that would not be, that's a good question, so that would not be supersymmetric then. So we can consider, that's a good that's a good question to play around with, right? So you can consider what would happen if W were a function of phi and by dagger, okay, and then the terminal Lagrangian is q squared of that. Now, when I hit this with q, okay, it's still 0, but when I hit it with q tilde, you know, it doesn't give me 0 anymore, because this thing is not, if it's a function of both line by dagger, it's not annihilated. Okay, good. All right, so we've been working with superspace and with superfields, and in that language, things are very nice and compact, right? And so that really leverages the full power of supersymmetry. But when you come to real life, say with supersymmetry breaking and the SSM, etc., to calculate anything of value, you have to go into components. Okay? So you have to break this down, and then things get a little bit messy. All right. But so we should really understand what this looks like in components, and that's how we're going to make contact with the things we already know, like the Lagrangians for scalar fields and permanent fields. Okay. So let me leave this up. And now we're going to go into components. Alright, so to go into components, we need to flesh out all the different components of a Carl superfield. Okay, so far I've only written the independent degrees of freedom, and I haven't written the derivatives, so now let me write them all out. And sneak in a few squares of 2. So that is a Carl superfield in its full glory in components. Okay? And another good homework exercise is to derive this using both the component approach and using the superspace approach. And check to get the same answer. Okay? So if you really want to master the subject, or technically get proficient in these kind of calculations, this is a really good exercise, is to try to derive this component expansion by imposing the constraint in 2 different ways. Check that you get the same answer. So you either impose a constraint with the superspace derivative, or you impose a constraint using the supercharge, like we did last time. Okay, this is what you'll find in like Weston Bagger, but this is entirely equivalent. All right. So okay. So now we stare at this for a second, and we want to plug this into. Well, let's start with the renormalizable case, which is simpler. Okay, so we want to plug this into the renormalizable theory. So let's start with the Kähler potential. I've been promising that these are the kinetic terms. So let's see how that comes about. Once we've written this whole thing out, it's not too hard to see. Okay, it's not too hard to see once I've written this out. So what is phi? Let's just do a single field for simplicity. So phi, what is the theta to the 4th component of phi dagger 5? All right, so if I really want to do it carefully, I would take this and its dagger, multiply it all out, cancel all the terms, get rid of all the terms that don't matter, and focus on the theta to the 4th. But let's just see quickly how that comes about. Okay, so how do I get a theta to the 4th by taking this and its dagger? Pretty much there are just 2 ways. Right? So here's a theta to the 4th. So if I if I multiply this times its dagger, I've already used up all the thetas, so I can only take it from here. Right? So one term in this is going to be phi dagger box phi. And factors of 2. Oh, I don't know. There's some factors of 2 and stuff, which I'm sure have to work out. You see, I can get it 2 different ways, right? I can get it from box phi and phi dagger. I can also get it from box phi dagger phi. So there's a factor of 2 there. I don't know where the other factor of 2 went. Ah, the other factor of 2 is here. Sorry, I lied. Yes. There is another way to get theta to the 4th. Yes. Yeah, sorry. So there's another way to get theta to the 4th from here. All right, I went too fast. So this is one way to get theta to the 4th is when this thing marries the dagger. Okay. Now I also have a theta bar here. I can get a theta to the 4th when this thing marries itself. Okay, and so that gives me a 1/2 when I work out the sigma matrices here. Okay, so all right, so this thing also gives me well, yeah. So this thing can also give me theta sigma mu theta bar, theta sigma mu bar, d mu phi, d mu phi, theta to the 4th. Okay, and so there's some gymnastics with simplifying this out. So when you take the theta to the 4th of this thing, it becomes eta mu. Is sort of the only thing it could be. And then maybe a half. Okay, altogether it becomes the usual kinetic term. Okay, I'm not really selling the factors very well here, but you see how you get the derivatives. All right, so that's one thing. So that takes care of these parts of the Carl superfield. And what about the fermions? Right, so I'm going to erase all this now and just write it as the usual kinetic term for phi. Okay, for a complex scalar field. And so that takes care of the scalar part of the Carl superfield. Now what about the fermions? So you see this has the answer in 2. So here I have theta squared theta bar. So to make a theta to the 4th, I have a theta bar from here, after I take the dagger. Right? So from here and here, I get, and I have one derivative. I have one derivative of psi. Okay? So that's the usual kinetic term for a fermion. Right? So I get from here, and those cross terms. Okay, and that takes care of this and this. And now I'm just left with this fellow, theta squared f. And so what is special about that? So when I multiply this times the dagger, I get f dagger f. Right, so as promised, the f component has no kinetic term. Right, these are the kinetic terms, they have derivatives for a scalar and a fermion. F is a scalar field, but has no derivatives. So this is no kinetic term. And so this is the auxiliary group. Okay, any questions? No? Okay, so that's how it works for the canonical Kähler potential. And it's a short jump to the most general Kähler potential, actually. Which, let me write it here. So let's consider the most general Kähler potential. So I claim that to take the theta to the 4th component of this, it's actually like no work at all. Okay. And the reason is that to get a theta to the 4th component, I have to take phi dagger phi. Okay, I don't get it from phi squared, I don't get it from phi dagger squared. The only way to get theta to the fourth is from phi dagger phi. So this thing is literally just the derivative of k with respect to phi dagger, and then the usual kinetic terms. Okay? Which, so this thing here is usually called, written like this, G, so, okay, it's written in a few ways. K phi dagger is one way. Two derivatives of the Kähler potential give me what's called the Kähler metric. Okay? And so another way to write this is G phi dagger times the kinetic terms. And so where this thing is now just a function of the lowest components. And so here we recognize the nonlinear sigma model. Right, it's a linear sigma model, I think, without this, and then this is the general nonlinear sigma model. Right? Okay, this is why it's the nonlinear sigma model. And this thing is called the Kähler metric. And that's where all this Kähler nonsense comes from, right? Is because this thing has the structure mathematically of a Kähler geometry. Okay, anytime you have, yeah, so it's a Kähler geometry. Okay. So that's one half of the story, is the kinetic terms. And more generally, the nonlinear sigma model kinetic terms. Okay, so to complete the story, I also need to, so we've done now the Kähler potential. Now we need to work out what the superpotential gives us. And we have the complete Lagrangian in components. Okay. So I'm going to erase this now. All right. So I want to be able to take d2 theta of w, which is just a function of phi. And let's just think about how I can achieve that. Okay, how do I get 2 thetas out of phi? I can either take it from here, an f component, right? Or what's another way I can do it? From a function of phi, I should say. I can take it twice from here. Right? If I have a phi squared, then I can take it twice from here. Right? So I either take it from here, or I take it from here. Okay, so what this gives me is I take it once from the superpotential, then I peel off the f, or I take it twice from the superpotential, and I peel off 2 fermions. Now you see the structure of the Pala coupling starting to emerge. Right? Also a mass term for the fermions. Okay, so a useful exercise, well, okay, let me do that as an example in a moment. Okay, so now I can erase the components. So okay, so let me put all this together. So we have L is equal to K phi dagger of d phi squared plus phi bar sigma mu phi plus f dagger f plus f plus squared phi squared phi sine plus their complex conjugates. Okay, and that is my full Lagrangian in components. All right, so there's one more step to go before we're done, because right now this thing does not look like, I don't see the potential. Like there should be a scalar potential emerging from this, right? So what do I need to do to get the scalar potential out of this? So there's something here which doesn't need to be here, right? The auxiliary fields are redundant, right? They're just quadratic, right? So what happens when we just have a quadratic thing in the Lagrangian with no derivatives? A bunch of quadratic terms in the Lagrangian with no derivatives. Those are Gaussian what? You can integrate them out exactly, right? They're just Gaussian division through. Right? So F and F dagger are just Gaussian integrals, and you can integrate out. And what's their equation of motion? It's just the derivative of this with respect to F. And so the equation of motion is F dagger equals minus dw d5. Okay? So with any Gaussian integral, you do the equation of motion, and you plug back in. Saddle point approximation is exact. Right? So when I do that, and I eliminate, so if I eliminate these two terms, it's just completing the square, right? And so these two terms become, so these two terms become what I want, which is the this is the scalar potential. Okay, so this is a general formula for the scalar potential in a supersymmetric Westphalian model. Okay, it's the derivative of the superpotential squared, absolute value squared. And then if it's a non-trivial Kähler metric, you should divide it out by that. And I'm doing this for a single field, so it's interesting to think about what happens for a general set of fields. And so this thing becomes the inverse of a metric, instead of just 1 over this thing, right? Okay. Oh, sorry, this may have confused you. This is, there should be a 1 over k here. All right, so I'd like to just work out an example here, this example here, so you can see how this works. Before I do that, are there any questions about these manipulations? Yeah.
In explaining the sequence, what's stopping you from taking 2 roots from the hector and then 1 from the scalar and then not from the scalar?
Sorry, say that again. 2 what from the other?
Could you not have 1 hector and 1 fighter in getting your this way?
That's what this is, I think. That's what this is. Yeah. Yeah, this is taking all the thetas from just one of the f's, and then everything else is the lowest component. Oh yeah, so you might be confused by what I'm doing here because I'm being a bit fast and loose with the superfield and its lowest component. Okay, but here, for instance, I'm specializing down to the lowest component of the superfield. Okay, that might be confusing, but it's standard to use the same notation for a superfield and its lowest component.
So you differentiate with respect to the superfield and then set the remainder that's equal to.
Yeah. Yeah, so if you really want to write this out in full detail, I differentiate W with respect to the whole superfield, of which it's a function, and then I set capital Phi equal to its lowest component, which sometimes I was calling little phi, but sometimes I'll just call it big phi. It's not the same thing. Okay, good. All right, so if you're confused, maybe let's just work out one example, which is the normalizable theory, and you'll see how the standard normalizable interactions emerge. Okay. Okay. Examples of normalizable theory. Let's just do a single field phi for simplicity. Okay. So K is equal to phi dagger phi. W is equal to f phi plus f m phi squared plus 6m phi cubed. Okay. And so the interacting part of the Lagrangian, okay, so the Kähler potential just gives me the kinetic terms, right? And the interacting part of the Lagrangian has this piece here. Let's just do that one first. Okay, so that's two derivatives of W, and then side side. So L has two derivatives of W, which is m plus a half and the phi. Oops. Yeah. So okay, I'm going to be using the standard convention again, not to distinguish between the lowest component of the superfield and the superfield. Okay. Let's see if we can get into that. Okay, so that is what this gives me. And so we recognize what? We recognize the mass term for a Weil fermion, right? And the Yukawa coupling. So fermion, mass term, and Yukawa coupling. All right, and of course I should have a confidence boundary for this. Good, and then now let's do the this contribution, which came from integrating out the auxiliary field. That is the scalar potential, so that doesn't involve any fermions, so it's a pure potential for the scalars. And so that is the derivative of W squared. So the minus sign here is as it should be, right? Because the Lagrangian is L minus V, right? So the potential should have a minus sign in front of it. That's for a positively pure potential. Okay. So all right. So the potential is just this piece here. I take one derivative of W, and what do I get? I get F plus M phi plus the half lambda phi squared, all absolute value squared. And that's good. That's what I want. So, well, okay. If there's no F here, the F actually is very important. We'll discuss the F later. But if there's no F here, then I see the mass term. See the mass term, right? M squared phi squared. And I see phi cubed interactions, and I see a phi to the fourth. All right. I also see that the fermion and the scalar have the same mass. And what else is not, it doesn't stop there. Supersymmetry also relates the Yukawa coupling to the phi to the fourth coupling. It's the same lambda, right? And so it's that magic, both the masses being the same and the lambda, the Yukawa and the phi to the fourth coupling being the same, that leads to, that solves the hierarchy problem. It cancels like the stop loop and the top loop, or the Higgs loop and the Higgsino loop. Right? It's the relation on both the couplings and the masses imposed by supersymmetry. Okay. The F here is interesting because if I don't take care of it, it leads to a tadpole. Right? It leads to a linear term in phi, which means that to minimize this, I should actually shift phi to get rid of the F. Right? So to minimize this potential, I should shift phi to get rid of that f. That would give me a minimum of this potential, right? And we'll see in the next lecture that sometimes it's not possible to shift phi to get rid of the f. And what happens when it's not possible? That's supersymmetry breaking. Okay, so supersymmetry breaking happens when you can't shift away these f's. Okay. So you see, for a single field, you can only shift it away, so it's okay. There's not supersymmetry breaking. So to get supersymmetry breaking, we're going to need more than one field. If it's going to be a wrong last one. Okay, so I'm supposed to finish now.